Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
When you think about modern technology, electricity usually takes center stage. Every smartphone, laptop, or server is powered by the flow of electrons. But hidden inside those electrons is another property, one that rarely gets talked about. The electron's spin. And that spin could completely reshape the future of computing and information storage. Spintronics, short for spin transport electronics, is a field that doesn't just use the charge of electrons the way traditional electronics do. It also taps into their intrinsic spin and the magnetic moment that comes with it. This opens the door to devices that can be faster, more energy efficient, and capable of storing information in entirely new ways. You've already seen some of the early impact of spintronics without even realizing it. The reason your computer can pack terabytes of data into a small drive, small enough to fit in your backpack? That's thanks to giant magnetoresistance, a breakthrough discovery in spintronics that revolutionized data storage back in the 90s. That one innovation alone reshaped the digital age by making huge data centers and portable devices possible. But researchers believe that's just the beginning. Spintronics could eventually enable memory that doesn't vanish when power is cut, processors that generate far less heat, and even entirely new kinds of quantum-based computing. It's a field where physics and engineering meet, and where the smallest building blocks of matter can rewrite the rules of technology. I'm Drew, and today we'll explore what spintronics is, how it works, where it stands right now, and its future, and the challenges that it will face before it can power the next generation of devices. At the heart of spintronics is a deceptively simple question. What if electrons could do more than just carry charge? Every electron has a built-in property called spin. It's not literally spinning like the basketball on your finger. Rather, it has a tiny magnetic orientation, like a microscopic compass needle, pointing either up or down. In the study of electrons, that orientation is just as real and measurable as charge, and it can be manipulated, flipped, and aligned. For decades, electronics has focused almost entirely on charge, pushing electrons through circuits the way water throws through pipes. Spintronics changes the game by adding a whole new layer of information to work with. Not just where the electron is or how many are moving, but how they're moving. So what does this actually mean? Let's step back for a second. Every material we interact with has electrons. In most materials, those tiny compass needle orientations cancel each other out. One electron points up, another points down, and the magnetic effects balance. But in certain special materials, like iron, cobalt, or nickel, large groups of electrons all point in the same direction. This alignment is what makes those metals magnetic. If you've ever held a fridge magnet, you've felt the result of billions of electron spins lining up together. Every day, magnetism is the most familiar example of spin in action. Now compare that to how a traditional computer stores information. A standard flash drive, for example, uses electric charge. It keeps electrons trapped, or not trapped, in tiny regions, and that presence or absence corresponds to a digital binary value. But the charge has some drawbacks. It leaks over time, which is why flash memory can eventually lose data. It takes energy to move charges around, which is why devices heat up, and it can be disrupted by radiation or extreme conditions. In contrast, spin-based memory could store that same 1 or 0 by flipping the orientation of spins, up for a 1, down for a 0. And because spin is a stable property, it can remember even when power is turned off. In short, measuring spin is so powerful because it provides a reliable, energy-efficient way to encode information. Another key part of the story is how spin and magnetism interact. When you pass a current of electrons through a magnetic material, the spins don't all behave the same way. Some spins, say the up ones, travel more easily than the down ones. This imbalance can be measured, controlled, and used to transmit data. It's like a traffic system where cars of one color get the green light while cars of the other have to wait. By controlling spin traffic, engineers can design new kinds of sensors and memory devices. You might wonder, why didn't we always use spin? And the answer is that detecting and manipulating spin at small scales, even as small as to the individual electron, is incredibly difficult. Charge is easy to measure with a current meter. Spin requires precise materials, thin films, and often quantum-level effects. Only in the late 20th century did scientists start to discover reliable ways to use spin, such as in the phenomenon called giant magnetoresistance. a discovery that earned a Nobel Prize in 2007 and paved the way for modern spintronics. From a physics perspective, spintronics is exciting because it blurs the boundary between classical electronics and quantum mechanics, the study of ultra-small foundations of the physical world. On one hand, you have electrons flowing through wires. On the other, you're dealing with a fundamentally quantum property that can't be explained by simple classical pictures. It's a reminder that even the everyday technology inside our laptops or smartphones is built on the deep laws of the quantum world. For students and physicists alike, the important takeaway is this. Spin provides a new way to carry, store, and manipulate information. While traditional electronics move electrons like marbles in a maze, spintronics flips their internal arrows, opening an entirely new design space. It's not about replacing charge, but about adding an extra dimension of control. And once you have a new dimension to play with, the possibilities for faster, smaller, and smarter technology expand dramatically. Now that we understand the basics of electron spin, let's look at how engineers actually use it in real devices. Spintronics is not just a theory. It's already powering some of the technology we rely on today, and it's paving the way for a whole new generation of computers and memory systems. One of the earliest breakthroughs in spintronics came from giant magnetoresistance, or GMR. In the 90s, researchers discovered that by stacking ultra-thin layers of magnetic and non-magnetic materials, they can dramatically change how easily electrons flowed, depending on their spins. Essentially, the layers acted like a gate that either allowed electrons to pass freely or made it hard for them to move, depending on how the spins were aligned. This effect was a game-changer for hard drives. It allowed engineers to pack far more information into the tiny magnetic domains on a disk, leading to a massive increase in storage capacity. Without GMR, today's smartphones and laptops wouldn't hold nearly as much data as they are able to today. A related concept is tunneling magnetoresistance, or TMR. This takes advantage of quantum tunneling, a strange but real quantum effect, where electrons can move through an insulating material instead of being forced to go around it. By carefully designing the magnetic properties on either side of this barrier, the resistance changes depending on spin alignment. TMR is the foundation of magnetic random access memory, or MRAM, which is one of the first commercially available spintronic memory technologies. MRAM is fascinating because it combines the speed of traditional RAM with the non-volatility of flash memory. Picture a memory cell like a light switch. Once you flip it on and off, it stays in that position, even if the power goes out. The battery backup. MRAM cells is by aligning electron spins, rather than relying on stored electric charge. That means computers and other devices can boot instantly, consume less power, and tolerate extreme conditions like radiation and space. A reason why MRAM is being used in the harshest conditions. Engineers control spin in MRAM devices by using tiny electrical currents, or magnetic fields, flipping the spins from up to down to represent binary information. The cells themselves are incredibly small, measured in nanometers, and arrays of millions of these cells can store huge amounts of data in a tiny chip. Because the spin orientation is stable, MRAM can also handle repeated writing and erasing far better than traditional flash memory, which degrades over time. Beyond memory, researchers are exploring spin-based logic circuits, where electron spins do the actual computation instead of just storing data. These devices promise ultra-fast, low-power processing because they don't rely on constantly moving charges. They could eventually power the entire processors, or even neuromorphic chips that mimic the human brain's networks. In short, spintronics devices take the tiny arrows inside electrons and turn them into powerful, reliable ways to store and process information. From hard drives to MRAM to next-generation logic circuits, controlling spin allows engineers to build machines that are faster, more durable, and more energy efficient than ever before. It's a subtle shift from conventional electronics for the user, but one with the potential to change how almost all of our devices work. Spintronics might sound like something far off in the future. In fact, it has a crazy name, but it's already being tested and deployed in specific, high-demand situations where its unique advantages matter most. Research groups and companies across the world are actively experimenting with new devices, refining materials, and looking for the best applications where a spin can outperform charge. One of the strongest footholds for spintronics today is in space technology. Traditional memory systems are vulnerable to radiation, which can flip bits and corrupt data. That's obviously a huge problem for satellites and spacecraft, where repairs aren't exactly convenient. MRAM, because it stores information in spin orientation rather than fragile electric charges, is highly resistant to radiation. that makes it extremely reliable for aerospace companies and agencies like NASA, which are already testing MRAM-based systems for space missions. In the consumer world, companies like Samsung and Intel have invested heavily in spintronic memory research. The focus here is to embed MRAM directly into processors as a replacement or supplement to conventional cache memory. The appeal is speed. MRAM can perform rapid reads and writes while consuming far less energy than traditional alternatives. For mobile devices, this could mean phones that use less battery and laptops that turn on instantly without waiting for boot sequences. Spintronics is also attracting attention in the field of AI hardware. AI systems rely on moving large amounts of data quickly, and memory speed often becomes the bottleneck. Researchers are looking at MRAM and other spintronic technologies as a way to create in-memory computing, where data is not constantly shuffled back and forth between memory and processors. Instead, the memory itself participates in the computation, drastically improving efficiency. Another promising direction is neuromorphic computing, building computers that behave like the human brain. Traditional chips process instructions step by step, but brains rely on massive networks of neurons firing in parallel. Spintronic devices, because they can maintain states without power and switch quickly between them, are being designed as artificial synapses. Early prototypes suggest they could enable low-power, brain-like chips, capable of learning and adapting in real time. Beyond computer memory, researchers are experimenting with a variety of types of spin-based sensors. These devices can detect tiny changes in magnetic fields with extreme precision. Applications range from medical imaging, where they could improve MRI scans, to geology, where they might help detect underground resources, or even to defense, where they could serve as ultra-sensitive navigation systems that don't rely on GPS. The common thread across these efforts is that Spintronics is carving out a niche where today's electronics struggle, whether that's surviving in extreme environments, speeding up memory, reducing power consumption, or mimicking the adaptability of the brain. While we're not yet at the point where every smartphone or laptop has spintronic processors inside, the fact that these devices are already leaving the lab and are entering specialized real-world use shows that the technology is maturing quickly. If today's spintronic devices are just scratching the surface, the future potential is far more dramatic. Researchers envision a world where spin, not charge, becomes the foundation of computing. That shift could enable machines that are faster, more efficient, and even more intelligent than what we rely on today. One of the most exciting directions is the current research that is working to develop spin-based logic circuits. Right now, computers rely on billions of tiny transistors that switch electrical charges on and off to represent binary digits. In a spintronic future, those binary states could instead be represented by up or down. If researchers can reliably build logic gates out of spin, it would open the door to processors that consume far less energy, because flipping spins requires less movement of electrons compared to pushing charge through wires. Building on that, Spintronics could drive ultra-fast, low-power computers. Today, data centers use enormous amounts of electricity to run and cool servers. Spin-based processors could dramatically cut that energy demand. For everyday users, it could mean laptops that run silently for days without charging, or smartphones that don't heat up during heavy use. Another frontier of it is the integration of Spintronics with quantum computing research. Quantum computers rely on fragile quantum states that are easily disrupted, making them hard to scale. Sometimes scientists believe that spintronic devices, because they already deal with quantum properties of electrons, could bridge the gap between classical and quantum computing. For instance, controlling electron spin at room temperature could lead to hybrid systems where quantum effects are harnessed in a stable, scalable way. Perhaps the most imaginative vision lies in neuromorphic computing, powered by Spintronics. Again, this is the system where Spintronics would power computers that work kind of like human brains. Such systems could revolutionize fields like robotics and AI, enabling machines that don't just follow instructions, but genuinely adapt to new environments. Of course, these advantages aren't limited to high-tech labs or AI. Spintronic memory might make smart devices that are always ready, without waiting to load or sync. Spin-based sensors could improve medical diagnostics by detecting diseases earlier or monitoring patients with less invasive equipment. Even transportation might benefit. Cars and planes could use Spintronics-based navigation systems that don't depend on satellites, making them more reliable in remote or obstructed areas. Looking ahead, the question is less about whether Spintronics will matter and more about how far it will go. The foundation is being laid with MRAM and experimental devices, but the horizon stretches toward a computing landscape that could look entirely different from the one we know today. If charge-based electronics give us the digital age, spintronics may well usher in something new. An age of machines that are not only faster and smarter, but fundamentally reimagined from the quantum level up. The path forward is far from straightforward. Turning the unique physics of electron spin into practical devices faces some serious challenges that researchers are still working to overcome. First limitation is material science. Spintronic devices often depend on exotic or finely engineered materials, such as ultra-thin magnetic films or carefully layered structures that must be manufactured at the atomic scale. Producing these materials consistently, and at a cost low enough for mass production, remains difficult. Even small imperfections in the alignment of atoms can disrupt spin signals, making devices unreliable. Another barrier is signal detection and control. Charge is easy to measure with a simple current meter, but spin is much harder to read out. Devices need highly sensitive techniques to detect whether electrons are pointing up or down. And maintaining spin coherence, the ability of spins to stay aligned without scattering, is especially challenging at room temperature. In many experimental setups, spin signals decay too quickly to be useful for real-world computing. There are also integration challenges. Modern electronics are built on decades of optimization for charge-based transistors. To replace or even supplement those systems, spintronic components must interface seamlessly with existing technology. That means new fabrication methods, new architectures, and new standards, all of which will take years to refine and scale. Finally, there's the issue of energy and scalability trade-offs. While spin flipping is theoretically efficient, many of today's prototypes still require relatively high currents or magnetic fields to operate, which cancels out some of those expected energy savings. Scaling spintronic logic circuits to the billions of components needed for a full processor is also unproven, and it may take entirely new engineering breakthroughs to reach that level. In short, while it holds immense promise, spintronics is not yet a turnkey solution. Researchers will need to solve fundamental problems in materials, detection, integration, and scalability before spin-based devices can fully move from specialized niche into everyday technologies. Spintronics is more than just a clever twist on existing electronics. It represents a fundamental shift in how we store information, not only as the movement of charge, but as the orientation of something deeper in the electron. From the hard drives that transformed the world in the 90s to MRAM already orbiting above us in satellites, spintronics has shown that it can solve problems traditional electronics struggle with. At the same time, the road ahead is not without obstacles. Materials, scalability, and integration with existing systems are all challenges that must be solved before we can move beyond specialized use. Still, history suggests that when physics and engineering align, breakthroughs follow. Transistor once seemed fragile and impractical. Now it underpins everything in modern life. Spintronics may well be on a similar trajectory. Whether it leads to computers that turn on instantly, smartphones that last for days, or entirely new ways of thinking about technology, Spintronics offers a glimpse into the future of tech, one where quantum properties are no longer hidden in theory, but harnessed in the tools we use daily.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.